All right, everyone. I am here with Rishabh Agarwal. Rishabh is a research scientist at Google Brain. Rishabh, welcome to the TWiML AI podcast. I'm looking forward to digging into our conversation. We'll be talking about your work broadly, as well as your NeurIPS 2021 outstanding paper, Deep Reinforcement Learning at the Edge of the Statistical Precipice. Great title. But before we dive into that, I'd love to have you share a little bit about your background and how you came to work in RL.
Back in undergrad, I think DeepMind released their Atari results. And as an undergrad student, it was really cool to see like, oh, we can play these games without any sort of hard coding and you can just learn how to play these games. So it combined like two of the interests I had back then, which is playing games and being able to do that automatically. So like I decided to take like ML courses back then in undergrad and then started to get interested more and more in research. And I tried a bunch of different things before coming to RL. And I think it really happened. So my bachelor's thesis was on learning how to play Scrabble. Uh, and basically, Scrabble, I think the best agent in Scrabble is something from MIT, which uses some sort of heuristics and Monte Carlo research. And we are thinking, well, can we replace these heuristics with a learned agent? Because think about like it's basically hard coding some sort of strategies to do when you are in a certain position. And we're saying, can we learn these sort of things? Because we can collect data from multiple self-play games and whatnot. So in some sense, what we were trying was trying to do something like AlphaGo, but on Scrabble. And this was like around the same time. It's just that we didn't have the same amount of compute. So we had to resort to like imitation learning and other kind of approaches.
Okay.
But this is how I started doing RL. It didn't really go well, but after that, I applied to a bunch of these residency programs at these different companies and got into Jeff Hinton's team. And I think one thing which Jeff Hinton told me was very like interesting. He said, "Well, I've seen a lot of people with a lot of papers already before they start research. Your case was interesting because you have done a lot of research and you have failed, so you know how research can be. And this is something I think you would need in a researcher. That research can be quite hard a lot of the times." And it's better to know or see failures early rather than later on, because if you don't see failures early on, then you'll think the research is easy and you just have to like do some things and publish papers, but it can be quite tricky. And he was like this is the kind of quality I was looking for, at least in a researcher I was trying to hire.
Oh,
That
wow.
was good to know that, well, someone do appreciate failures too. So I worked there as a resident in the brain team for a year in Toronto, and there I worked on mainly RL, I think. And after that, I moved to Montreal, and I'm doing RL research still because I like doing RL. I think I've tried moving away, but RL is just too exciting to. So I just keep coming
Nice.
back to RL.
You mentioned you tried a few areas of research besides RL before settling into it.
Right.
What were some of those?
So I think the first research project I had done was something about disambiguation, which is think about like a lot of these things are already solved by large language models these days. But think about, let's say I say I'm going to the bank. Now this could be a river bank or it could be a bank where you collect money, right? And without actually additional information, you can't really say which bank were you talking about. Most likely the bank where you go to collect money, but it might be the river bank too. And we're thinking about, well, how do you actually figure out, or how do you come up with word embeddings that can give you some sort of probabilistic sort of embeddings, which are like, depending on the future sentences or future words you see, you will change your embedding in some sense. So it's not a static embedding. It depends on where this word is. So this is the first thing. Then I think dabbled a little bit in meta learning, or how do we classify, I think, things quickly, because back I think it was 2016, and back then meta learning was starting to get popular, and it was interesting to see if we can generalize like one shot or two shots. So things like, I think if I give you images of dogs and cats, and now can you generalize one shot to, let's say, different breeds of dogs, then what is in your data set, given like a few examples. So these are the sort of things. But I think the aspect of RL which was much more interesting was that the agent can learn from its own mistakes rather than a static data. And I think that was something which was quite cool, because this is something we as humans also do, that if we don't know how to solve a problem, we try to figure it out, collect some data maybe, and then just solve it, or like make attempts at doing so. But this is not something which happens in supervised learning. So I think that was the aspect which made me think about RL. Plus, we play usually games in RL, so that was another interesting thing.
And within the realm of RL, is there a particular area that you like to focus on nowadays?
I have in the past focused on offline reinforcement learning quite a lot, but more recently, what I've been trying to think about is that a lot of the problems we tackle are sort of we have, let's say, a sort of problem, we learn an agent and forget about it, then we try to improve and come up with another agent. But a real world problem is not like that. A real world problem remains in existence for a few years. And it's almost always the case that you don't forget about your previous agents. You always try to build up on top of that. So think about, let's say you have a YouTube recommendation system and the algorithm recommend you videos. Now, let's say you have another algorithm which can learn like better recommendations. You wouldn't really just throw away your existing policy or agent or whatever behavior you have learned and try to learn everything from scratch. What you really do is you try to build on top of whatever existing policy or agent you have. Now, this is good, and this is mostly the case for applications, but in research, we don't really follow this sort of protocol. Like really, we have a benchmark, we try to come up with an agent, and we solve this, and we try to improve on that benchmark. And we're saying, well, why don't we really do this in research? So this is something I've been trying to focus on, that how do we come up with sort of problem settings and methods which can build on existing things. And these existing systems does not have to be like human demonstration. They might be just like your existing agents which learn. So think of like an example which I quite like is think of Minecraft and think of some agent which has some basic capabilities to do build basic structures in this Minecraft. Let's say build a house or something like that. Now, if you take that agent, can it expand quite a lot, and can it do like much more than just building a basic house? Things like take existing agents and improve them significantly, as opposed to learning new agents entirely from scratch. And I think this is valuable if your problem either takes a long amount of time or it's just not feasible to do things again and again. So if I don't know if you know, so OpenAI had this project on Doda where they basically spent 10 months of training to get the agent to beat the grandmasters there. Now, the thing was, in their paper, they have like an interesting figure where they say we never really started from scratch, because if we did, it would have taken us like 5 to 6 times more like months, so like apparently more than 40 months to just get this agent. And I said it was really expensive to do so. So what they always did was whenever they had to, and the reason they had to do this was because their environments kept on changing. So their observation space or things like whatever their input is, it kept on changing, and they had to make sure that their model still works for these changes. So, and they could not really afford to like just throw away the model. So what they kept on doing was they kept adding more components to their existing model so that it can reuse whatever they have learned, but also handle the existing change or the new changes which come into their pipeline. So that was like an interesting use case of this sort of setup. But this is more of a one-off example of research, I think, because they have to tackle a practical problem, they had to do this. But if your benchmarks really just take like, I don't know, a day to tackle, probably people are not interested in. But I still think there is value in this sort of research paradigm of building on top of existing agents. Well, this is something I think I've been excited about for a while now.
Nice, nice. And you're speaking about it broadly. Have you thought through kind of a taxonomy of approaches? Like it has echoes of transfer to it. It has echoes of hierarchy, like OpenAI, has echoes of like initialization, even, taken simply.
Yeah, so this is a pretty broad topic because what you transfer really, like, it depends on, for example, what you transfer. Do you have a policy? Do you have a value function? Do you have a model? Do you have an exploration strategy? Also depends on how you transfer it and what is given to you and what not. So there are a lot of these things. So really, it's like a much bigger paradigm. It's just that what we're saying is typically in research, what we do most of the times is we start tabula rasa. But that's something we don't have to do. Like at least for a lot of the problems, we don't do tabula rasa, at least in practice. So why are we doing that in research? And we should be moving away from this. So I think in our head, it's really broad, but we'll probably start from focusing from a narrow like problem, and then hopefully the community thinks this is valuable, and maybe they pick it up from there.
Got it. Sounds like you're early and you haven't specifically or narrowly formulated a problem statement just yet.
We do have something, but I think it is so it's related to, let's say, I guess we had some desiderata, which was let's say I give you a policy or an agent, and I have to use an off policy agent or something which can exploit existing data, because that's something which is useful. Now, can I quickly recover this policy's performance or agent's performance while actually continuing learning? And I think the interesting aspect here is this policy is not optimal in any sense. It's just some sort of good policy. It can get you some good rewards or behavior, but really you want to improve on it. So the dependence of your agent on this policy or this existing, let's call it teacher, should be limited. Like at some point, you know that you should have to learn on your own. Like kind of like how we take learn anything. We take lessons and then we learn on our own. We just don't keep taking lessons forever. Similarly here, yeah. So think of it like your instructor, right? Like your swimming instructor teaches you swimming, but let's say you went on to become like a gold medalist or something. So I think you definitely learned a lot on your own rather than just relying on your instructor all the time. So something along those like that you have to let go of your instructor so that you keep learning on your own because you know that maybe you can do better than your instructor. And
Mm-hmm.
so that's the sort of I think concrete setup we are in. But yeah, it's still in the works and we're still thinking about what to do with this.
The paper that I mentioned earlier, DRL at the Edge of the Statistical Precipice, as I mentioned, it won an Outstanding Paper Award at this past NeurIPS, but it wasn't necessarily the paper that you were trying to write when you started out on your research program. How did that paper come to be?
Yeah, there's an interesting backstory. So I think what happened was I was trying to use this benchmark called Atari 100K, which is an interesting benchmark where they say that, oh, we'll train an agent for 100K interactions, which is approximately 2 to 3 hours of human gameplay. And this is the amount of time which the human agent was given or the professional human game player was given to get like some sort of score on all these games. So this is the baseline we use when we compare with respect to humans on these games. And the benchmark said, okay, let's do this. Let's actually train our own agents to this much amount of time and see how well can we compare against human or how well we do compare to humans. So this is good. This is like a good benchmark because it gives you like an estimate of how sample efficient your agent can be or like how fast can your agent learn. So this is all good. And I was coming up with like maybe a better approach to do this sort of thing. I ran my agent. I like get some sort of variation. I thought maybe I should just increase the number of random seeds so that I see less variation in my results. I doubled the seeds. I still see a lot of variation. I kept doubling the seeds, and at some point, I think I was at 30 seeds, and I was still like the variation is huge, and it's all over the place. And but then I looked at the existing literature, and I saw everyone used 3 random seeds, and they were comparing the results and claimed soda and whatnot. And in my own results, what I was seeing was that there were seats which led to really worse performance, and there are seats which were beating state of the art, depending on what seats I end up using, right? And this was concerning. So for a moment, I thought maybe
And
it's
the
the method.
implication is that the published results that you were referring to are kind of cherry picking runs that did particularly well.
So
In a
rather than that,
sense.
it was more like it's unclear if the published results actually hold if you ran a lot more evaluations. So it's like it's
Mm-hmm.
unclear either they underperformed their actual reported results or overperformed them. So that was something which is not clear. But so initially, I thought maybe it's. So I think the interesting artifact which happened in my own work was that if I kept adding more seats, my numbers or results kept going up. And
Oh,
I'll tell you the story about why that happened too. But
yeah,
my it was just like interesting to see that I went from 3 to 5 to 10 to 20 to 30, and my just
yeah.
results kept improving. And I was like, I have not done any like change here. Really, the only change is evaluation. What is happening? So initially, I thought maybe it's just with the method I'm evaluating. So there were two paths here. One was just to skip this benchmark and go to some better benchmark and think about it. And the other was maybe there is something wrong going on here, and people have been using this benchmark, and probably they will because it is an interesting one. So why not try to fix it? So at this crossroad, we decided let's just stop the existing project we were doing and think about this other problem because it seems more fundamental. And this is, I think, something in research which we should learn that we should always keep an eye out for interesting opportunities. If you're really trying to go somewhere, it's okay to take like a turn or something along the way if that looks more interesting to you. Like it's totally okay to give up on that. So we decided let's focus on this other thing. So what I did was I had a bunch of baselines already coded up for the like the existing published results. So I thought maybe I don't trust my own baseline. Let me just ask the code from the authors themselves or whatever their open source code was, and let's just try to evaluate this code. And funnily enough, the same sort of things happened that the uncertainty in results was pretty huge. And for some of these methods, I again saw basically the more number of random seeds I use, the better the results were. and what was this issue? And then I think this hit me. Basically, what are we doing is we have an algorithm, we're evaluating it on a bunch of tasks and aggregating the results to do something. And in Atari, at least, what we use is something called median score. So if you have, let's say, I don't know, 20 tasks, what you use is the performance on the median tasks in some sense. And this was like a simple statistical fact that if you take median of expectations or median of averages, it's not going to come out be the same as average of medians in some sense. So basically, there's a difference between if you evaluate, let's say, a few seats, calculate the average score on each of the tasks, and compute the median. This is one quantity. The other quantity is you evaluate infinite number of seats. You really get the true average score you get on each of the tasks, and then take the median. This is another quantity. So the funny thing is, if you repeat the first process again and again, which is you have few seats, you evaluate the aggregate performance, and then just keep repeating this process to take an average, or in some sense expectation, this quantity is not equivalent to the true quantity you care about, because this is a biased estimator. Now, this is, I think, well-known statistical fact, but the funny thing was that the size of the bias can be as large as 30% of your performance itself. So it's possible that some of the results were just like reported just because of the bias, or you really didn't know that what's happening. And this is actually what we found.
What was it in the problem that you were solving that made that bias always an underestimate of the actual performance?
Yeah, so this was actually an artifact of the algorithm. So what happened was really like I really didn't tune my hyperparameters that well, so it hadn't overfitted. And because of that, it was actually like underperforming when I used few seats. And if I run more seed, it seemed to be better performing. But for some other algorithms, what we found that the direction of the bias was in the other direction, which is it could be positive or negative depending on the algorithm. So for some algorithms, if I add more seats, the performance went down as opposed to improving. So that this made it even worse, because if it was in the same direction, at least you can say my algorithms would improve with more seats. Now it was, some algorithms actually become worse and some algorithms become better. And the thing is, the bias is actually reasonably large to not say what's happening. So this is one of the issues, but it was not actually the big issue. The biggest issue was the uncertainty in these results was pretty high. So what actually happened here was like as I've seen, like my results were changing quite a lot, and sometimes the difference in the results from 3 seats and let's say something like 20 seats was as large as the difference between the previous soda and the baseline. So it was a huge gap to see. Like maybe this gap can make your conclusions like it's unclear if your conclusions are published method actually was better, or was it due to just statistical fluctuations? And so that was an issue. So we thought, well, this is not so expensive benchmark, and I am at Google, so we do have a reasonable amount of compute. Let's just try to use that compute to see how much fluctuation there is. And that led to like the first finding of the paper that there is an enormous fluctuation, and most of the existing methods actually overreported. Their results were like overestimated in some sense, except one method, for funnily enough, which actually underestimated. So there's also one method which was like, if I evaluated on more seats, its results would have been much better. It's just that they didn't do so. But the interesting bit was that most of the results were actually quite overlapping, at least in terms of these median scores. And it was unclear if there is an improvement. And all of these were published papers in the last couple of years. So papers at ICML 21, and some of them were actually at NeurIPS 2021 too. But
and were there implementations published, or did you have to kind of engineer their implementations?
So most of them were actually published, except one for which we had to implement. So this was really not on. So we are trying to like remove all sorts of confounding factors. That this is our issues. It was really we just took their open source code and just ran it on a lot of seats, and we saw, oh well, there is actually a lot of overlap and whatnot. And so this was the problem part of things. And I think it was sort of, at least a lot of people, researchers in RL know of these problems, that there are problems when we compare RL methods and there's a lot of fluctuations and whatnot. So this was the first part. But then I think we thought about it and we realized that, well, we were at Google and we could have, we launched these 100 seats for all these methods, but this is not computationally tractable for anyone outside Google. And even at Google, it was pretty expensive to do. So each time, let's say you have to compare your method, you wouldn't be launching, 100 seats. And it also becomes like, and this was like a simple benchmark, or at least a computationally relatively inexpensive benchmark. If you had, let's say, a harder benchmark, Let me give you some estimates. So for Atari games, like the Atari 57 benchmark, it takes about 1,000 GPU hours for computing like a single result aggregated across all the tasks. And so this is about, if you launch all the like runs in parallel on all the games, it'll take you about 3-4 days with like existing open source libraries. So that is a lot of time to just get like one result.
And by one result, you're talking about training an agent for a particular game in the Atari suite.
So no, it's like training an agent for the standard 200 million frames for all the games,
Okay.
and doing like, let's say, something like 5 seats. So let's say this is the minimum you're going for. This will take about 3-4 days, assuming you have done parallelization also. Now you can't really expect researchers to run 10 seats or 20 seats or a lot more seats, because it quickly becomes a lot more expensive. But the thing is, at least like in reviews, we often see this. Like we often get requests from like reviewers saying, well, we've only validated on 5 seats, why don't you run 5 more seats? And it's very like hard to like convince them otherwise, but it is really expensive. And I think this was the problem I also had at the back of my mind, because I have gotten reviews like these and I couldn't just say, hey, it's really expensive and it'll take like 5 days just to get 5 more seats. And so how do I convince that these results are statistically robust while not running a lot more seats? Because that's not really the solution. And I think this problem will become worse as we move on to harder benchmarks, because these are like so Atari games are actually 20-year-old, I think, or 40-year-old. I don't exactly remember, but they are pretty old. And now, if you think about, let's say, more recent and harder problems, let's say you think of something like StarCraft, then suddenly evaluating even just a handful of seats is pretty hard. So I think the problem of few seats and like really expensive benchmarks is going to stay, or at least more and more researchers would end up using fewer seats and more difficult problems.
I'm curious if there's a correlation between the number of seeds the reviewers asking for and the size of their company. Like the Google reviewers
uh,
are asking for more seeds.
That is possible. Although we did have one plot in the paper where we showed the correlation between as time passed and the number of
Mhm.
seats we have used, while our benchmarks have become more complicated. So I think back in the 80s, we were using something like
Mm.
30 seats because our benchmarks were really simple, maybe mountain car, cart, like really simple simulated problems. And now I think as we introduced this Atari benchmark, we started using like fewer and fewer seats.
Right.
And more recently, I think we've been using just 3 to 5 seats. That's the sort
That
of
would
standard
support
we
your
have.
idea that it's out of necessity as opposed to
Yeah.
negligence.
So yeah, it's not really people are trying to hide. It's just that it is expensive to evaluate these models and like get like these results. So people
Mhm.
run whatever like the prior work follows. So okay. So we had this mindset that, oh, people are going to evaluate few seats and they still want to compare across these algorithms. Now, how can we do this robustly? And this was the question we had. The solution we went on to was something which we already do in computer science, but not in machine learning, which is they just plot the distributions of the score you get across all the tasks and all the seats. So think about it for again. So what are they doing is, so this is commonly done for comparing optimization software, which is how fast they're able to solve the problem. So what they do is you have a bunch of problems, they run their software or algorithm on all these problems, they get times for each of them, and now they just plot the distribution of how fast they were in this, like to solve the problem. And they just distribution meaning something like the CDF of all the times they got across all the problems and all the runs. And this is cool for multiple reasons, but I'll cover that. But we thought, oh, why don't we do this in RL also? That basically the nice thing, at least in RL typically, is that when we have a bunch of tasks, we usually have some notion of score comparisons across tasks, which is, at least for Atari, for example, we use human normalized scores, which is all the scores are relative to humans. So we often compute, that's why we are able to compute aggregate scores also, which is what does it mean to aggregate scores across two different games, which might have really different score ranges. So think about, I don't know, pinball versus something like Pong. The score in Pong goes up to 21, while in pinball, it can be a million or something like that. Now, you really just can't compare their scores, but if you normalize the scores, let's say relative to humans, now it makes sense to actually compare scores in Pong and, let's say, pinball. You can say how bad I'm doing with respect to humans on both of these games. Now, this is a cool property. So we thought, well, why don't we just mix all the scores we get and just compute like the distribution? And this gives you something called performance profiles. Now, there are a bunch of cool things about these profiles. These profiles are nothing fancy. These are really just the CDFs of the distribution you would get if you were to mix all the scores. Now, the nice thing about these things is that the area under these profiles would be actually the mean score you get across all the games. Similarly, if you compute, let's say, you draw a line at y equal to zero point 0.5, then you'll get the median, the point where these curves intersect. And you can also similarly get the any sort of percentile. So because it is just giving you the entire distribution in a single picture. And the other nicer thing about these profiles is that you don't really have to like write out a big table with like a bunch of methods. So let's say Atari has 57 tasks. So what your table would look like is 57 sort of rows, and then for each row you have multiple columns. And oftentimes what happens is if you have more than 4 or 5 methods, you will just not report standard deviation or variance because space constraints and whatnot. And then it's even harder to compare because some methods are doing better in some class and not in others. So these tables end up going in the appendix most of the time. And like really what you end up reporting is in the main paper is some sort of aggregate measures, but the aggregation hides a lot of the things. So we said, well, why don't we report these sort of distributions? And this was the first sort of solution. The funny thing, the solution to the problem of, well, how do we do better? But the actual solution was more or less something like we should report the statistical uncertainties we have when we run these algorithms. So think about this. Whenever you're running an algorithm on a bunch of tasks, what you're trying to evaluate is a random variable because the performance really depends on the randomness of whatever thing you evaluated. Now, each time you change your random seed, your performance would changes. So really what you have is a random variable and you're trying to evaluate it using a finite number of samples or seeds in this case, right? So what you should be really reporting is also what is the uncertainty in this variable, which is if you were to repeat your experiment, let's say with a different random seed, what is the result you expect? And now the thing is, some people say, well, maybe we'll just fix the random seeds and that's okay. And I'm saying, well, it's not really okay because let's say I go to a different hardware, then suddenly just fixing random seeds wouldn't really fix the randomness. And also, I think the bigger reason against just fixing random seed being the solution is why should I prefer seed 123 over seed, I don't know, 42 or something like that. These were the problems. We said, well, let's report uncertainties. And now the nice thing again, by mixing all the tasks and the runs, you still get a decent sample size, which is let's say you have a single task and 5 seeds. Really reporting uncertainty with 5 seeds, you can't really do much because you just have 5 samples to sort of report some sort of measure of what is the variation. But let's say I have 5 seeds and 10 tasks. I have 50 samples now. And now you can actually think about doing something with these 50 samples and reporting like uncertainty now starts to make sense. And for that, we went on to something called statistical bootstrapping, which is I think the first time I used bootstrapping in a different context than in than the way we typically use in RL. But it was basically, I guess, without going into details of what it is doing, but the main question we were trying to answer was we have finite data and we are trying to evaluate a random variable. We're saying we should also report what is the uncertainty we have, which is if we were to evaluate the same algorithm again with maybe different seeds or under different random conditions, what are we expected to get? So this is why we went on to the solution of confidence intervals. And there's a fun fact which I learned through while going through this. So apparently in statistics also, so there were other options also, things like p-values and whatnot, which people use in other areas. But the main journal of statistics in the US actually bans thresholding p-values. So people often say my result is significant, statistically significant or not statistically significant. But I think there's a catch there, which is it's like you say, oh, if my p-value is less than 0.05, then it's statistically significant. But if my p-value is 0.051, then it is like not significant. And that is an issue. The other thing is your improvement or whatever you're reporting is actually statistically significant, but not practically significant. Maybe it's a really trivial gain. And I don't really care about if it's significant because it's like, I don't know, it's a 0.0001% improvement or whatever you're doing. So really what you want to see is what is your effect size in some sense, like what are the possibilities of gains you expect without thresholding. And then if you really care about statistical significance, you can also glean that from a confidence intervals. But I saw like at least in rest of the statistics and other areas also, there was a push for confidence intervals as opposed to using these p-values. Plus p-values are also harder to grok. Like these are something which makes this paper harder to read, I think, in some sense. So that's why we went on with the solution of confidence intervals.
And so does the confidence interval. You're asking researchers to publish these confidence intervals in conjunction with their RL experiments. Is that replacing asking them to also publish the distributions, or they complement one another?
Yeah, so they are both complemented. So apparently your distribution node also have a confidence interval. So the funny thing is, think about it, which is if you repeat your experiment with a different set of seeds, your distribution would also change. So in some sense, your CDFs, and this is why I think we say don't use something like, or that's why we didn't propose something like a box plot, because your distribution itself has uncertainty. And if you plot the CDF, you can also plot the confidence bands around your CDF. So really, like reporting uncertainties is one of the key things. We are saying don't report these point estimates. So what people typically do is they report a single number, which is saying this is my aggregate result across my benchmark. We are saying, oh, no, 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 there is actually some uncertainty in your aggregate result, and it can be large, it can be small. So it's better to just report this uncertainty also, so that we have some idea of how high variance this algorithm is and how significant maybe the improvement is. So, but yeah, so think about basically any sort of result you obtain from a finite number of seeds is a random variable at the end of the day. And now there is some uncertainty associated with, so there is some sort of confidence interval associated with that. And that's why I think so. And yeah, so this is the sort of view we take, that if you just start thinking about random variables, a lot of things make sense. So maybe I'll present like one metric which we do proposes. So think about the question of comparing two algorithms. Really what you have is you have two random variables and you have a bunch of samples from both of them, and you're trying to ask me which random variable is better than the other. Now, if you think about it this way, then the natural thing which will come to your mind is, well, what is the probability that this random variable is better than the other random variable? And that's it. You really just can compute this probability. Now, what you have is you don't have the distributions. You just have the empirical distributions. But there is a way to compare the empirical distributions, which is you just do pairwise comparisons for whatever points you have, and you get a probability. Now, here's the fun bit: this probability itself is a random variable, because if you repeat your experiment, your
Uncertainty.
probability changes. So there is a confidence band. Even though this is a probability, there is a confidence band around this probability too. But this metric is a cool measure because it directly asks the question, okay, what is the probability that your baseline or your method beats the baseline? Like if you're saying or claiming soda, you can just evaluate this probability itself. It does not care about, so the downside is it does not care about the effect size, which is your method can be 1% better or 100% better. It'll still have the probability of 1. But it at least asks this direct question of, okay, am I doing better than the baseline? And gives you like an estimate of what is the likelihood that this is happening. And you can glean a lot of the things. So surprisingly, so this was the second metric. And I think the third metric, we realized that so proposing or plotting distributions is cool, and that is good for qualitative comparisons, but it's unlikely that a method is or like a new algorithm is going to outperform another method in distribution across all the tasks and all the samples. It's likely that these distributions would overlap at certain point, and all these things would happen. So eventually, I think, or researchers will resort to some sort of aggregate comparisons in some sense. So we thought, well, okay, let's talk about aggregate metrics here, which is what do we use? We use mean or median. And this is common. This is common across machine learning, that whenever you have a benchmark, yeah, there are these are the two sort of metrics which are really prevalent everywhere, that either we report the mean performance or the median performance. Now, at least in RL, I think mean is not so common. The reason being there are few tasks which can be really high performing, or your algorithm can be really high performing on some of these tasks, and mean is just dominated by these outlier tasks. So let's say you get a score below 1 on almost all the tasks except one, where you get a score of 100. Now, mean score is just dominated by that one task. So typically in RL, we prefer this median score because it's more robust. But the fun thing about median is if I set the score to be 0 on half of my tasks, the median score wouldn't really change. And so what kind of robust measure is this where I can just really just crash in half of my tasks and it wouldn't really reflect any sort of change? So these aggregate metrics are somewhat misleading. So here again, we looked back at statistics and we said, well, what we can do is we can really, again, think about we have, I don't know, maybe 5 seats and 10 tasks, so 50 numbers. We can compute something like the interquartile mean, which is like somewhere in between the mean and the median, which is the mean of the middle 50% of the numbers you have. So the middle 25 runs. And now this has like best of the both properties of the mean and the median. It cares about all the tasks in some sense, and it also is robust to outliers like median. but it has nicer properties and whatnot. So this is something we propose, like in general, that when you're trying to report aggregate benchmark performance, there's something you can do. But that's it. The caveat is that the aggregate really hides a lot of the information which was given to you by the distribution, which is aggregate is talking about a specific property. So maybe I'll give you one sort of anecdote related to this. So on Atari, at least, typically what papers have focused on is median scores or median normalized scores. Now, the funny thing is we have algorithms which are improving on the median normalized scores, but we said let's come up with this metric called which is a better version of mean, which is optimality gap, which is how far are we doing with respect to the humans. So rather than really talking about what is your average performance, let's talk about how far you are from the humans. So lower is better. So 0 means you're really close to the humans, and 1 means you're really random, like you're as worse as you can be. So this is a metric we computed for all these existing algorithms. And funnily enough, what we saw that a lot of these recent algorithms were improving in terms of their median performance or mean performance, but they are doing worse in terms of their closeness to human performance, which is in some sense they're getting better on a lot of the games, but they're also doing worse than humans on a lot of these harder games possibly. So that was
Mm.
something interesting. And this is what happens, I think, when we really focus on a single metric in some sense. And that's a downside of like aggregation. But I do think aggregation is sort of a necessary evil because it's really hard to compare. I don't know, if you have a lot of tasks and results, it's really hard to compare the distributions or these tables. And people would want to report some sort of aggregate measure, but aggregation has this harms.
I was just going to jump in and ask, since publishing this, have you seen the community kind of take up these additional measures and include them in their own research and publications?
Yeah, so we have seen some pickup. Still pretty early to say what would happen, but I do think at least I have seen some pickup of this recently, and like some of these IClear submissions and some of the neuro submissions themselves. And I think the reason the community would like to pick this up is because it's really not asking you to do anything extra other than just evaluating your results more thoroughly. And we also released actually a pretty good open source library. So you just give me your raw numbers for doing this. So yeah, I think the reason we did that was because we realized if we just say these are all the things you do, it takes some work to actually implement some of them. And people are not going to do that if that's something additional they have to do. So we thought, well, let's just come up with a library so that you give me your numbers and it'll just do the thing for you. We even released the plotting scripts because I think we got uh, like some appraise for the kind of plots we had in the paper. And we thought it might be better actually if other researchers can use these kind of plots also.
And so the library, you just kind of call it in your training loop and it's recording your.
No, no, it's not even doing that. So it's like you do whatever you're doing in your training loop. At the end of the day, you were reporting performance. Also send these numbers to the library. It'll just give you a plot back. And then that you can put directly in your paper without any like changes, sort of. So that's so I think we try to make it as easy for people to use this. Now, there's a bigger question about is there any incentive for researchers to do this? Because that's a tricky one. But I do believe, I think a lot of us are at least trying to do good science. And if people are
Yeah.
aware of these sort of issues, they will go towards using them. A lot of us are trying to publish. And I guess those people may be more worried about, oh, if I report these uncertainties, my results don't look as good as they did without these. But the reality is, like, these are the actual results. Like the uncertainties are really just telling you, oh, this is the randomness you have in your reported result.
Can you maybe qualify or characterize the when you looked at the existing algorithms? Did you find anything particularly surprising or dramatic in the reported results, or was it kind of like there's a lot of variation here and you don't really know, but it's not something that kind of fundamentally changes the way you think about a particular algorithm?
I think some of the rankings were even flipped in the because of the uncertainties. That you see that the uncertainties for one method are really like much larger than the other, and it's likely the other thing I think you'll think is a lot of the changes we were able to publish are actually not really resulting in an improvement. It's just that happened that there were random fluctuations, and you ended up getting it's almost like cherry picking, but not exactly. But it is something along those lines that there were enough random fluctuations in the setup that it's likely that you benefited from that. and because of that, the paper was able to being popular. If you look at the empirical results only, then it's possible that the method is not really doing any better than soda.
You're saying that some percentage of papers didn't really need to be papers.
In some sense, yeah. But I guess those are the papers which really depend on just the empirical evaluation. I would say most papers really are not, here's my method, here's like 10 different benchmarks, I evaluate them, my method is better, except I don't think those are the kind of papers, or at least a lot of the papers are like that. Papers really have a lot of going on. They have some sort of argument why this is a good algorithm or why this paper is worth publishing. And I think the empirical results are only the supporting evidence for all that. I don't think we are trying to sell the algorithms as being the best. What we're trying to say is, oh, here's a good method, and here's another argument for why this is a good method in some sense. So I don't think there's any downside of reporting uncertainties. It's just that I think the maybe as an author you might feel that the reviewers would not like this if my method is not really beating everything straight out of the, like, I don't know. It's like they feel hiding this sort of information is better than actually presenting it. But the sort of reality is that if someone else was to run their algorithm, then they need to know what is the variation is in their method, because it's possible I'm not able to reproduce their results. And the reason was as simple as, oh, I ran on a different GPU. So this happened on, I think, with one of the things I was trying. So what happened is, at least in TensorFlow and JAX, you can't really set the random seed because there are some operations on GPU which have randomness and which can't really be fixed. Now, this was the only change in my code base. I evaluated 100 seeds for a single method twice. And what I saw that was the correlation between the results was something around minus 0.2 to 0.2, which was like really tiny correlation. Basically, just like this, setting all the seeds for really just one change of GPU randomness made randomness really a big issue eventually in my results. So there's a huge change even with like small randomness. And maybe it's like a butterfly effect in RL that initially you collect different data and then you different updates and whatnot, and it expands. But this sort of issues, I think, after our paper, and I think concurrent to our paper, there were other works also which point out similar issues in vision and natural language processing in fine tuning these pre trained models. They say that it really depends on what exact model you use and all these other hyperparameters we set up. So it's just like I'm saying, reporting uncertainty is more truer to reality. It might make the results look slightly worse, but this is what the reality looks like. And now, if you deliberately try to hide reality, that is like so. I think ignorance is okay. Like I think most of the researchers were really sort of not aware that these were the issues, because some of our own papers had reported these point estimates, which is we said, here's a benchmark, here's an algorithm, here's the result we get, and we just compared them. But now we are aware that there is a huge uncertainty in these sort of evaluations. So we would be more willing to report these sort of things to showcase, okay, what is the uncertainty, or at least try to make sure that our results are robust statistically. That is like, and that's, I think this is also one of the reasons we see these papers that say, oh, here we evaluated a bunch of these SOTA models and nothing really holds up in these applications, or actually on a controlled experiment. And the reason is it's just because a lot of the times you're not reporting these sort of uncertainty measures. And we thought like these methods were actually better, but they really were not in some sense.
Mm-hmm. Mm-hmm.
Yeah, one point I want to say is like, so I think the actual incentive for doing all this is doing good and reproducible science, but I don't think that's really a strong incentive. The better incentive would be if conferences, for example, try to enforce this, and they do to some extent. So if you look at NeurIPS checklist, for example, they do ask that, have you reported error bars? And now the funny thing is, people do report yes to that question, but also not report error bars when it comes to things like aggregate metrics, because like it's harder to think of, oh, this is an overall result across all the tasks. What does the error bar mean here in some sense?
And does the effect of the kind of randomness we're talking about, is it outsized in RL due to the kind of repetitive nature of it relative to, vision, NLP, other things?
Yeah, I feel so. There are like two kind of So I feel that is the case, and there are two sources of it. One is when you collect your own data. So it depends really on where you are at, and if there was some randomness, it will sort of aggravate more over time, because this randomness affected what was the initial data you collected. And then the second source is we are learning from our own predictions in some sense. Whenever we're doing off falsy learning or Q learning. And if you're, so it really highly depends on what your initial estimates of whatever the function you're learning was. So and I think both of these amplify like the randomness. So definitely, I think it's more prevalent. But then again, there are cases like I was talking about NLP earlier. So when you do fine tuning a pre-trained model, they find that there is actually a huge uncertainty there again, depending on, for example, simple things like what was the order of the samples you fine tuned on, or what was the exact checkpoint you used to fine tune. So there are like probably, so I think any area where these sort of statistical considerations can have large influence, it should be the case that we report uncertainties. So I don't know where did I see this, but I saw like a paper where they said that even on ImageNet, if I just trained a ResNet model, the variation is something like around plus minus 1%. So it's a Gaussian distribution, but depending on the seed I pick, my result can be 1% or better or 1% worse. And this is a huge number if we are talking about ImageNet, because people publish results with like 0.1% of differences and whatnot. But yeah, coming back to incentives, I do think it's unclear what are the actual incentives for researchers to publish or at least report do these things. Because if it so rigor makes publications or harder to publish in some sense, and sometimes it does make it easier if your results are really great. But most of the scenarios, it will have problems, and researchers might not want to be more rigorous so that they can publish easily. So there is this trade-off, I think, which shouldn't really be a trade-off. But if you're really going for, I want to publish this paper, then I think you may not want to report uncertainties and whatnot. So that's something we are not clear on.
Where does these uncertainty measures that you're proposing here, how do they fit into kind of a broader I'm imagining that others have published things that they also think that papers should all include, and how many of those? How long is that list, and where does this fit in that list in terms of potential impact on the field? Do you think?
Right. So I think there were a lot of things we took into consideration when thinking about these metrics, and we said let's try to do or at least build on what people already actually do. So
Mm-hmm.
people already actually report some sort of aggregate performance measure, at least in RL.
Yeah.
And we said, what's the minimal change we can do rather than going to like complicated statistical tests and what all those things. People already want to report some sort of standard deviation, and oftentimes they do. So if you use mean, for example, it's easy to compute the standard deviation. Now, the thing is, when you think about median, people haven't reported any sort of uncertainty measure. And the reason is it's unclear what the standard deviation would look like or how would you compute it unless you are willing to use, let's say, more advanced statistical bootstrapping tools. So I think this was the reason, or at least this is maybe one of the reasons that we typically don't report uncertainty measures, because we already do if we are able to do them. It's just that once your metric is not as straightforward as mean, then I think it's become unclear how do you actually even calculate the variance. And real, because the only way to do so is to simulate your distribution and see what the variance looks like. And so I think my, and at least our understanding of the tools we propose is and also some of these tools are already in use in computer science. Like I've been saying, like the sort of motivation for these performance profiles came from a paper published in I think 2000, which is I think the standard for optimization software in computer science. They already use some of these tools, and these are like tried and tested tools. It's just that maybe we can also adopt them in ML. Now, I think the sort of the question you're asking for that, I feel there might be better ways around reporting uncertainties, for example, because we just propose like the simplest possible measures which we can do, and we tested their like correctness on some of the tasks. But it's possible that there might be better ways to report uncertainty, which are more correct in some sense, or let's say theoretical guarantees around this. Also, I think some of the problems which we don't tackle is, let's say I give you a single task and you really have 3 4 seats. What do you do? Like, I don't think our paper really talks any about that, but that is a common setup. I don't really have a benchmark. I just have 2 3 tasks and I want to compare these algorithms. What do I do to do like better comparisons in some sense? And that still is a open problem, I think. But with regards to where does it fit, I would say it's really the high level message of the paper is we should be reporting interval estimates of things. And here are some tools which we have developed for you to use. But There might be other ways also to do this, and please feel free to do so. I don't think you should be using these specific tools if you feel that's not the right way to go, but you should be reporting some measure of uncertainty. I think this is the high level message. The maybe the only advantage of the tools is you don't really have to do anything extra than what you have been doing, like no extra logging, no extra sort of seed evaluation and whatnot. It is really geared towards few seed and like multitask settings.
Awesome. Well, Rishabh, thanks so much for taking us through that. Very cool work, and congrats again on the award.